The following Zoom session is being recorded and will appear later today on my YouTube channel, Math with Mayo. Therefore, when you participate in the Zoom meeting, if you do not wish for your picture or your name to be made public, please leave the video off and use an alias name. If you have questions during the meeting but do not wish to speak, email me at bmail@ybcc.edu and I'll respond as soon as I can. Alrighty, so today we're going to go on and cover section 11.2. But before we do that, we have some questions from section 11.1, starting with number 21, which says the following: let f of x equal 1 over x and g of x equal 1 over x squared. And then it says, find the following: f composed with g of 5x. So first of all, what does f composed with g of 5x means? It means we need to find f of g of 5x. All righty, that's the first step. Now we need to figure out what g of 5x is. And so over here where we have the g of x, g of 5x equals 1 over. Remember, every place there is x in the original function, we're going to replace it with 5x. So I get 5x, the quantity squared, which is 1 over 25x squared. 5 squared x squared. Okay. So then all of that goes right here. So now we're going to find f of 1 over 25x squared. So then we're going to put that in here, also in there. So we get 1 over 25x squared, which is 1 divided by 1 over 25x squared, which is 1 times the reciprocal, which is 25x squared over 1. And 1 times 25x squared over 1 is 25x squared. So your final answer is that. Any questions on that? Karina or Antonia, any questions there?
No, answers my question. Thank you.
Okay. Let's take a look now at number 22. It says let h of t equal the square root of t plus 9 and k of t equal t minus 2. Find the following: h composed with k of 9. So h composed with k of 9 is h of k of 9. K of 9 is 9 minus 2, which is 7. So we replace k of 9 with 7. So now we have h of 7, which goes up here and becomes the square root of 7 plus 9, which is the square root of 16, which is 4. So h composed with k of 9 equals 4. Next up is number 23. We good to go on?
Yes.
Okay. Let's see. Let h of t equal the square root of t plus 5 and k of t equal t minus 9. Find the following: k composed with h of negative 4. So that's equal to k of h of negative 4. h of -4 is equal to the square root of -4 plus 5, which is the square root of 1, which is 1. So that goes in the place of h of -4. So now we have k of 1, which goes up here, which is 1 minus 9 or -8. So k composed with h of -4 is -8. We good to go on that?
Yes.
All righty. And finally, number 24. Number 24 says, if f of x equals x squared plus 4 and g of x equals 3x squared minus 9, show that f composed with g of x is not equal to g composed with f of x. Simplify your answers completely. So basically, we're showing that in general, composition is not commutative. Okay. Now, let's see here. It has a bunch of responses. It doesn't just have the final answer. So let me do this. Give me a second here, and let's put this up on the same screen. So hang on here. So now you can see 24. And sometimes when there's these fill in the blank things, it gets kind of tricky. And basically, I guess the best thing I could say is go ahead and just do the problem and then go back and see how you could fill things in. Okay. All right, hang on here.
Yes, that's what I did, was fill in the problem and then went back.
Yeah, because otherwise it gets kind of tricky. So what we're supposed to do first of all is we've got f composed with g of x, and that equals f of g of x. Okay, and g of x is this, so that would equal f of 3x squared minus 9. So that's what you put in this first response here, because it says f of, so you'd put your 3x squared minus 9 in there. Okay, and then what do you do with that? You take this and you put it in, wait a second, my bad. Okay, hang on. Why is it not letting me erase it? Well, this is fun. That's not what I wanted. Ah! Okay, we're gonna get through this together. All right. You can see I enjoy these as well. So then what would you do with this? This would go in
the place
here,
yeah.
Right? So
Yes.
you get 3x squared minus 9, the quantity squared, plus 4. And that's what you're going to write here, the quantity something. So you kind of have to figure out, what is it that they want here that fits the pattern. Okay. And then finally, you're going to multiply this all out. So you're going to get 3x squared minus 9 times 3x squared minus 9 plus 4, which is 9x to the 4th minus 27x squared minus 27x squared plus 81 plus 4, which is 9x to the 4th minus 54x squared plus 85. And so that's what goes down here in this bottom one right there. Okay. You following that? Antonia, you okay with that?
Yes, I am over here.
Yes,
Antonia? Yeah.
yes.
Okay. And then the second part is basically the exact same thing, only you're going the other direction. So you've got G composed with f of x equals G of f of x equals G of x squared plus 4 equals 3 times x squared plus 4 squared minus 9 equals 3 times x squared plus 4 times x squared plus 4 minus 9, which is 3 times what? X to the 4th plus 4x squared plus 4x squared plus 16 minus 9, which is 3 times x to the 4th plus 8x squared plus 6 minus 9, 16, excuse me, which is 3x to the 4th plus 24x squared plus 48 plus 9, which is 3x to the 4th plus 24x squared plus 50. Oh, it's a minus 9. I changed it to a plus 9. Plus 37. Okay. And so you've got this and this and then finally this. I wrote 37, it's 39, my bad, sorry. So again, with this fill in the blank things, you kind of just have to ignore it, do the problem, and then look and see what it is they're looking for. Is that making sense?
Yes.
Okay, Tony, we good? Okay, we're going to go on now to section 11.2, and I'm going to switch back to the other screen. So give me just a minute here again. Yeah. Okay. All right. Okay, we're back to the normal whiteboard screen. Excellent. So let's go back and look at what a function is. One way of describing a function is with some mappings. Let's say we have 1, 2, 3, and 4, and we have 5, 6, 7, and 8. Okay, and we'll always have the domain on the left and the range on the right. Actually, let's see, let's put another number in here. Wait, let's do this. Okay. So if I say 1 goes to 5 and 2 goes to 5 and 3 goes to 6 and 4 goes to 7, this is a function, right? Each value of the domain goes to exactly one value in the range. Okay, so that's a function. Any questions about that one? All right, let's say we've got this. 1 goes to 4, 2 goes to 5, 2 goes to 6, and 3 goes to 7. How about this? Is this a function? No, it's not, because you've got one input going to more than one output, so it's not a function. Okay, are you all right with that? Now, if I have a situation where each value of the domain goes to exactly one value in the range, and each value in the range comes from just exactly one value in the domain, this is what's known as a 1, 2, 1 function. Okay, so each value in the domain goes to one value in the range, each value in the range goes to one value in the domain, that one-to-one correspondence. That doesn't exist here. even though it's a function, it's not one-to-one. And here, it's not even a function. So this represents a one-to-one function. There's the same number of domain values as range values, and there's a one-to-one correspondence between them. Okay. Now, there are some special things about one-to-one functions. And one of the things is that one-to-one functions have what is known as an inverse function. So let's go back to this situation. 1, 2, 3, 4, 5, 6, 7, 8, where we've got this one-to-one correspondence. Okay. Going this direction represents a function. We'll call that function f of x. We could go the other direction. We could start here and move in that direction, switch the domain and the range, and this would be what's known as the inverse function. Now, this notation doesn't mean f to the -1 power, which is 1 over f. That's not what it means. In this context, that means the f inverse function. So the inverse function of whatever f of x is, okay? So if f of x gets you this direction, f inverse of x gets you that direction. The domain of one becomes the range of the other, and the range of the one becomes the domain of the other. We're going back and forth the other direction. The best example I can think of is going from Fahrenheit to Celsius, and then going from degrees Celsius to degrees Fahrenheit. One of them takes you in one direction, the other one takes you back the other way. So they're inverse functions of one another. Okay, now, here, hang on a second. So for a function to have an inverse function, the original function has to be a one-to-one function. Okay, consider this. This is not a one-to-one function. Likewise, you couldn't go the other direction because it's not one-to-one going the other direction either. Actually, this isn't even a function at all, is it? Let's see here. This is the one I wanted. So, sorry. This is a function going this direction. But if we turn it around and went that direction, we'd have an input going to two different outputs. So it's not a function that direction. Okay. The only time it's a function in both directions is if it's one-to-one. Now, let's say we have a one-to-one function. F of x equals 2x plus 4. All right. So for each input, there's exactly one output, and for each output, there's exactly one input. If we were to graph this thing, f of x equals 2x plus 4. Let's see here. F of x equals 2x plus 4. Let's see, that has a slope that's 2 and a y-intercept that's 4. So we'd start right there and we'd go up 2 and over 1. Okay, so our graph would look like that. Now, this is a function because it passes the vertical line test. For it to be a one-to-one function, it has to not only pass the vertical line test, but what we call the horizontal line test as well. So this is a one-to-one function. For each x, there's only one y. For each y, there's only one x. Okay. Now, let's go back here and let's algebraically find the inverse of f. So we're going to find f inverse of x. It's a 4-step process. Step number 1, rewrite f of x using regular notation. So change f of x to y. Okay, step number 1, rewrite it using regular versus function notation. Step number 2, interchange all the x's with all the y's. Again, step number 2, replace all the x's with y, replace all the y's with x's. Step number 3, solve the new equation for y. I'm going to subtract 4 from both sides. Divide both sides by 2. I'm going to go ahead and write y on the left side of the equation. I don't need to, but I just prefer it there. Okay. And in fact, I could write that like this if I wanted to, I suppose. Okay. This is the same as this is the same as that. That's just in a nicer, more recognizable form. Okay. So step 3 was to solve the new equation for y. Step 4, replace y with the F inverse notation. Okay, so here's f of x, here's F inverse of x. Any questions about that? All right. I want to point out something, and we're going to come back and do more of these, but I want to point out, let's take f of x equals 2x plus 4, which we already graphed back here. And let's see if I can get rid of all these extra lines. Okay. And let's graph F inverse of x, which was 1/2 x, I believe it was minus 2. Okay, let's graph that. Here we have a slope of 1/2 and a y-intercept of -2. So a y-intercept of -2 and a slope of 1/2. So this is f of x, and this is F inverse of x. So we graphed the original function, and we graphed its inverse function. Now I want to draw the line y equals x. Okay, and I'm actually just going to make it a dotted line. Let's see if I can get this lined up here. That's the line y equals x. Okay. Can you see that these two lines are symmetric about the line y equals x? Okay. Also, let's go back to this f of x equals 2x plus 4. And let's just find some ordered pairs that are solutions. Okay, so let's make a table and let's do it that way. Let's see here. Whoops. Okay, sorry, I keep messing things up by touching the wrong things. There we go. Okay, so let's find some ordered pairs. How about we'll go -1, 0, 1, and 2. Okay. In fact, let's start our graphs over. Let's get rid of all these graphs. Okay. Oops, went too far there. Give me just a second. Okay, now let's find some ordered pairs for f of x. When x is -1, we'd have what? 2 times -1 plus 4, which is -2 plus 4, which is 2. Okay with that?
Yes.
If x is 0, 2 times 0 plus 4 is 0 plus 4 is 4. if x is 1, 2 times 1 plus 4 is 2 plus 4, which is 6. And if x is 2, 2 times 2 plus 4 is 4 plus 4, which is 8. Okay, so -1, 2, 0, 4, 1, 6, 2 8s off the graph, but we get this graph right here. Which is basically the same graph we had before, right? Y-intercept of 4 and a slope of 2. Okay, now let's find some ordered pairs for the inverse. And in this case, I want to use 2, 4, 6, and 8 as my x values. Okay, if x is 2, you'd have what? 1/2 times 2 minus 2, which is 1 minus 2, which is -1. Okay with that?
Yes.
If x is 4, you'd have 1/2 times 4 minus 2, which is 2 minus 2, which is 0. Let me ask you this. What do you think the values are going to be right here and right here? Any ideas without calculating them?
4 and 6. 1 and 2.
Let me say something again I said before. The domain of a function that's 1-to-1, the inverse function, that's the range. The range of a function that's 1-to-1, the inverse function, that's the domain. So the domain of f becomes the range of f inverse. The range of f becomes the domain of f inverse. Okay. So let's do a review, and then we're going to go back and look at a bunch more examples. If you have a function that's 1-to-1, there is an inverse function that's also 1-to-1 that you can find using 4 algebraic steps. And we're going to go through some more of those. If you have a 1-to-1 function and its inverse function, ordered pairs for f of x, if you interchange x and y, you'll have ordered pairs for f inverse of x. The domain of f is the range of f inverse. The range of f is the domain of f inverse. So the domain and the range switch places. If you graph f of x and f inverse of x on the same grid, they will be symmetric about the line y equals x. And there's one more piece to this puzzle. If you take a function and its inverse, so let's see here, f of x equals 2x plus 4, f inverse of x equals 1/2 x minus 2. If you take a 1-to-1 function and its inverse function and you compose them, in both directions, they're going to have the same answer, and that answer is going to be x. Remember I said earlier yesterday that in general, composition is not commutative, but in the case of where you're composing a function and its inverse, it's going to be commutable. Or commutative. Too many words. All right. F composed with f inverse of x is equal to f of f inverse of f is equal to f of 1/2 x minus 2, which is equal to 2 times the quantity 1/2 x minus 2 plus 4, which is x minus 4 plus 4, which is x. Now, what did I do? The same steps we've done in the past that we reviewed earlier today. F composed with f inverse of x is f of f inverse of x, but f inverse of x is all of this. So that goes in the place of f inverse of x here. Then we take all of this and plug it in for x there, and we get x. Let's go the other direction. Let's take f inverse composed with f of x. That's equal to f inverse of f of x, which is f inverse of 2x plus 4, which means now we're going to put that in there. So we get 1/2 times the quantity 2x plus 4 minus 2, which is x, plus 2 minus 2, which is x. Voila. So that's a way of proving whether two functions are inverses of each other. If you compose them in both directions and they both equal x, they're inverses. Okay. So we've got a lot of stuff going on here. A one-to-one function has an inverse function. We can find it algebraically. We can find it graphically. We could graph one and just reflect it across the line y equals x. We could take ordered pair solutions for one function, switch them around the x and the y, and get ordered pair solutions for its inverse function. We can compose them in both directions, and we should come up with x as the answer. All right, there's all of that. Now, let's go back to the 4-step process of taking a one-to-one function and finding its inverse function. Okay, let's take a look at this one. F of x equals 2x plus 6 all over 3. Okay, so 4 steps to finding its inverse function. Step number 1, replace f of x with y. All right. Step number 2, interchange all the x's and all the y's. Step number 3, solve the new equation for y. Let's multiply both sides by 3. Okay. Then we'll subtract 6 from both sides. Then we'll divide both sides by 2. Then I'm going to put y on the left side. You don't have to, but I'm just going to do that. Okay. Now, replace y with f inverse of x notation. And again, I could write it this way, or I could write it like that. These are the same. Okay. So this and this are inverses of each other. Ordered pairs from one, switch them, you get ordered pairs for the other. The domain of one is the range of the other. The range of one is the domain of the other. If you graph them, they'll be symmetric about the line y equals x. And if you compose them in both directions, they'll both equal x. Any questions about this example? All right. Let's take a look at another example. Let's see here. F of x equals x cubed minus 4. Let's find its inverse function. Step number 1, replace f of x with y. Step number 2, interchange x and y. Step number 3, solve the equation for y. I'm going to do that by taking the cube root of both sides. So I get y equals the cube root of x plus 4. And again, I'm going to write it with the y on the left side of the equation. Step number 4, replace y with f inverse of x notation. So here's the original function, here's its inverse. Any questions about that? We good to go on?
Yes.
All right. Let's see here. How much time we got? We got enough. F of x equals quantity x minus 9 cubed. So to find the inverse function, step number 1, replace f of x with y. Step number 2, interchange all the x's with all the y's. Step number 3, solve for y. Well, to do that, I'm going to have to take the cube root of both sides. So I get the cube root of x equals y minus 9. Continuing to solve for y, I'll add 9 to both sides. The cube root of x plus 9 equals y, or y equals the cube, whoops. The cube root of x plus 9. Finally, using, let's see here, inverse function notation, f inverse of x equals the cube root of x plus 9. And notice that plus 9 is not inside the radical. So here's the original function, here's its inverse. All right, let's take a look at, let's see here, the following. It says f of x equals x squared plus 1. And then it has this little thing in parentheses, x greater than or equal to 0. I wonder why it has that. Well, let's graph this thing. F of x equals x squared plus 1. Okay. Where would the vertex be? Anybody? Okay, that's fine. We'll find it. Think of this as in the form of y equals x minus h squared plus k. So the vertex would be at 0, 1. Is that making any sense? Because there's nothing inside the square but x. Anyway, the vertex is at 0, 1. And then let's find, let's see, if x is 1, 1 squared is 1 plus 1 is 2. So 1, 2. And if x is 2, 2 squared is 4 plus 1 is 5, 2, 5. Okay. So this is what the parabola looks like. Think back to the last chapter. Are we okay with this? It's basically x squared moved up 1 unit. Is this graph a one-to-one function? Does it pass both the vertical and horizontal line tests?
No.
It doesn't, does it? It's not a one-to-one function. But by applying this restriction, which would get rid of that, right? If we just used x values that were positive or 0, now we have a one-to-one function. So we've gone through and taken a function that wasn't one-to-one by putting a restriction on the domain. We've created a one-to-one function. Okay? You all right so far?
Yes.
Okay, now let's find its inverse function. Let's see here. want to make sure I have lots of room, so we'll just do this. So y equals x squared plus 1. Replace f of x with y. Interchange x and y. X equals y squared plus 1. Subtract 1 from both sides. X minus 1 equals y squared. I'm going to put y squared on the left side. Take the square root of both sides. So wouldn't you do plus or minus? So you'd get y equals plus or minus the square root of x minus 1. Right? Remember, take the square root of both sides of an equation to do a plus or a minus. Okay. You all right with that?
Yes.
Okay. So let's graph this thing. If x is 1, well, in fact, couldn't I just go in and say I'd have this, and then I'd have that, and I'd have that point, so it looked like that, and then the negative would look like that. I'm kind of skipping some steps here, but just suffice it to say, if I graphed it, it would look like this. But is that a one-to-one function? One I just graphed?
No.
It's not even a function, is it?
No.
Well, here's the thing. The domain of f is the range, and I should take this one step further. Okay. F inverse. The domain of f is the range of f inverse. So a restriction on the domain of f would be a restriction on the range of f inverse. So y has to be greater than or equal to 0, which means this piece isn't there. So we just have the plus. And now I have a one-to-one function and its inverse. So by restricting the domain, we took a parabola that's not one-to-one and created a function that's one-to-one. We found its inverse, but we had to apply a restriction that was on the domain of f to become a restriction on the range of y, or of f inverse, excuse me, to get a function and its inverse. Okay, so kind of keep track of domain and range and restrictions and whatnot. All right. Let's see here. Let's do another one. We have f of x equals negative 1/3 x plus 4/3. And we're going to find its inverse. Step number 1, replace f of x with y. Step number 2, interchange x and y. Step number 3, solve for y. So we'll subtract 4/3 from both sides. Then I'm going to multiply both sides by -3. So I'm going to get -3x plus 4 equals y. -3 times x is -3x, and -3 times -4/3. Negative times negative is positive 12/3, which reduces down to 4. Then I'm going to put y on the left. Okay. Step 4, replace y with f inverse of x notation. So here's f of x, here's f inverse of x. You okay with that?
Yes.
All right. Let's see. Let's do this one. F of x equals 3 over x cubed minus 1. So algebraically find its inverse function. Replace f of x with y. Interchange all the x's and all the y's. Solve for y. I'm going to multiply both sides by y cubed, which gives me y cubed x equals 3 minus y cubed. Okay. Still with me? Oh, but we need to solve for y. This is going to get tricky. I'm going to put all the y's on the same side of the equation. So I get y cubed x plus y cubed equals 3. We're going to use a trick that we used a long time ago in solving formulas. I'm going to take the left side of the equation and I'm going to factor out a y cubed. Okay, so I get x plus 1 left over. You see what I did there? Hello?
I'm lost on that one.
Okay, take a look at this. Y cubed x plus y cubed equals 3. What's the greatest common factor of those two terms? Y cubed.
Like,
And x plus 1 would be left over. Think back to chapter 6.
Okay, yeah, I got it.
Okay, good. Now divide both sides by x plus 1. Take the cube root of both sides. And I get y equals the cube root of quantity 3 over x plus 1. And finally go back or use inverse function notation. So here's the original function. Here's its inverse. That was a kind of a tricky one, wasn't it? Yeah. All right. Well, I'll be back this afternoon at 1:15 with an office hour. Should you have any questions, I'm going to go ahead and stop the recording.